Okay, good afternoon, everyone. If you have not yet received notification, so I posted an announcement on Canvas regarding attendance and marking and noting it yourself. There's a laptop in the back on the lab benches. If you have not read the announcement, which was posted just a few hours ago, you need to go into Canvas settings and enable notifications. Okay, so there are options to send it to your mobile devices. There are options to send it to your email, it's also a text SMS option. So please ensure that you do that, because oftentimes I will post an announcement and it will send a notification. So if you miss that, then you wouldn't know what's going on in the class. You should ideally enable this for all of your classes. Okay, so every single class, just come in there, laptop will be available at the back. Just go in there, the mouse is kept, just use the mouse and just mark yourself, note yourself. Okay, let's get to our notebook. Let's see which one. Second one. All right, that's the first page of our first lecture. So that. All right, so intro to EEE. It's not a term that I am very familiar with using because we always use EE. This term EEE stands for electrical and electronic circuits, or electrical and electronic engineering. So we deal with electric circuit analysis and a little bit of electronic devices. Here's the difference. When we say electric circuits, we are primarily referring to circuits built with resistors, capacitors, inductors, and the fundamental circuit theory or the techniques that we use to analyze these kind of circuits. Electronic refers to the semiconductor devices that we use in, well, nearly everyday life. That would include the diodes, transistors, FETs, logic gates, logic devices. So those all fall under the umbrella of electronics. Circuit analysis is the most fundamental of classes that an EE student takes. This is where they learn the techniques. And those techniques can be applied to simple circuits as well as electronic circuits, semiconductor devices, digital logic circuits, and all sorts of systems. So this class specifically was designed for the CPE major or the CPE student to understand circuit analysis, learn about circuit analysis techniques with a systems-based approach, meaning how you're going to apply it in a practical way. So the components that we look at in this class are primarily resistors. Okay, we learn about resistive circuit analysis. And then in the later portion, we'll also learn about diodes. Diodes is typically something that a EE student learns about in their third year when they get to 300 level classes, semiconductor devices. You will learn more about diodes when you take 3306, or you might take, well, next year when you would take a higher level course, okay, semiconductor devices. But in this course, in 115, what we're going to do is we're going to build circuits using diodes. So we just need a fundamental understanding of what a diode is, how it works, and what it does. Okay, so we're not going too in-depth into how a diode is created. We are not going into device physics. You're not learning anything of that sort in this class. We are simply looking at it as an off-the-shelf component, and how can we use the diode to build our circuits and devices, which is also something that you will do in the lab. Okay, so that's primarily what we do in the EEE class, electrical and electronic circuits. This is basically, again, a systems perspective. So from an application point of view. Okay, so right here at the top where it says what we need to do in order to learn EE. Well, EE, electrical engineering, deals with the generation, transmission, and usage of electrical energy. And depending on the application, that energy can be converted into multiple different forms. So for example, electrical can be converted into any ideas what kind of energy forms we can convert electrical energy to? Light. We have that example right here in the class. So light or optical energy. Any others? There's one passing right by the road. Mechanical. You had your hand up for mechanical. Okay, there's mechanical. Any others? Thermal. There are one or two more. But instead of giving you the answer, I'll let you think on that. So once you're done outside of the class, after a class, any other time, think on a couple more forms of conversion from electrical to any other form of energy. Okay. So it's primarily concerned with dependencies because you're trying to have a system, you have a function, the function might depend on something or some other function might depend on your function in your systems. So we're primarily concerned with dependencies. Hence, we do a lot of math where there are functions and then operations on those functions. Okay, so this conversion, the energy conversion requires a lot of interdependencies. In order to solve them mathematically, we use a lot of mathematical operations like summation, differentiation, integration, etc. Okay. Specifically in 215, you will learn about capacitors and inductors. So when you learn about capacitors and inductors, the voltage and current for a capacitor and inductor depends on time. Okay. And so because it's time dependent, we encounter derivatives and integrals. And in order to solve for those values, we have to generate differential equations. So the ODE, ordinary differential equations. But again, that's not for this class, that's for next quarter in EE 215. All right. So EEE systems, or EEE deals with systems where we implement complex functions. That's an automatically given statement. Systems are made up of tiny different parts. Each part or each component is connected into a network. In electrical engineering or in engineering in general, sometimes we use networks and circuits interchangeably. So in some cases, we might refer it to as a circuit. Some cases, we might refer it to as a network. And so in a way, we can say these two words are kind of synonyms or analogous to each other. Okay. But technically, circuit is simply a graphical representation of a physical system. Okay. So we use schematics to graphically illustrate or create an outline for our physical system, and that is known as a circuit or a circuit diagram. And those, of course, requires several different symbols to represent each one of those components. Okay. All right. So functions. What kind of functions are we dealing with? Well, we have constants, we have proportional, we have linear. And sometimes we have something that might not be a function at all. Okay, but primarily we are dealing with like resistors. Resistors have linear relationships between voltage and current. And so most of the equations or the functions associated with the resistive circuit analysis are linear. Again, when you get to like capacitors, capacitors and inductors, they are not, excuse me, They might not seem linear, like a capacitor and inductor might not seem linear because it's time-based derivative and integration. But a capacitor and an inductor also have a linear relationship between the voltage and current. And circuits created using these linear devices known as linear circuits. Voltage and current for a resistor have a linear relationship. I would say linear and proportional relationship. Okay, linear and proportional. V stands for voltage. I stands for current. So they are linear and they're proportional. Okay. The constant of proportionality for a resistor is the value of the resistor itself. And so from this, we can write an equation which is V equals I times R. V equals I times R. That's the constant of proportionality. Take a look at this equation for 5 seconds. Have you all studied this before in physics classes, right? What's the name of the person it's named after? Ohm. Anyone remember the first name? George. It was George Ohm. As also, it happens frequently in the world. A lot of people and a lot of scientists, researchers work on many tiny things. And so the work that is attributed to one person or maybe just one team is built upon the work of like tens of hundreds of people that came before them. But as it so happens, whoever makes like a grand discovery for whatever reason, maybe they make a invention or a theory presentation that radically changes their field, and then in honor of their work, it comes to be named after them. So George Ohm is the one who this equation is named after, so it's known as Ohm's law. But this work or this equation is also based on the work that was done by people that came before him. All right, so V stands for voltage, named after anybody? Andrew Volt. I don't know the first name, but it was named after Volta, or at least the units. Volts is named after Volta. I have to check on that Andrew Volt name. And then current units are amperes, and resistance, of course, the unit are. Units and unit prefixes are very important, so please keep those in mind when you're solving problems and presenting your work. If you have missing units, half a point would be deducted. So the units and these notations are interesting because voltage can be noted by uppercase V and lowercase v. The unit volts is always uppercase V. So volts is always uppercase V, whereas voltage can be represented using uppercase or lowercase v. Current is ampere, A, or amp for short, AMP, again, uppercase. And ohm is unique because it uses the Greek letter omega. This again is the uppercase omega, not the lowercase. So units typically are always uppercase, capital letters. Okay. This is the only quantity I can think of that actually uses the Greek letter as a unit symbol. Everything else is simply a letter. All right, symbol for a resistor is right here. So we use this symbol to represent resistance when we are creating our circuit diagrams. Now, one thing before we move on. We say that based on Ohm's law and based on scientific principles, that voltage and current for a resistor have a linear relationship. That is true. But again, in the real world, that is only true based on environmental conditions. Okay. For the most part, when we learn about theory, fundamentals of theory, we are always learning about theory based on room temperature or just the normal real world conditions. Okay. However, if the temperature increases to extremes, and when I say extreme, I don't even mean hundreds of thousands of degrees, just like, all the way just 100 or 200 degrees, this doesn't hold true anymore. Or if it goes below freezing, so if it goes to extreme plus or minus temperatures, Ohm's law may not hold true. Okay, so it holds true only for certain environmental conditions, what we call as room temperature, 75 to 80 degrees F. Other than that, extreme temperatures, extreme pressure, humidity, it would not hold true. Okay, functions of a single variable. We get a constant. Constant is basically showing us here, if we plot the voltage value for a ideal voltage source as a function of time, meaning you have a DC battery, for instance. You take a battery and you plot the value of that battery over a long period of time. The value of that battery or ideal battery voltage source will always remain constant. It will never change. Okay, so constant voltage source has a property, actually just an ideal voltage source. It provides a constant value of the voltage at its output terminals. And let's move this in. Okay. And when that happens, in electrical engineering, we also call that as a DC source if you plot it against time. Symbol for sources is basically a circle. It's a circle like this. It is a source, and the source is providing energy or supplying energy. Plus and minus symbols indicate it's a voltage, and arrow indicate it's a current. So in physics labs, have you all used DC power supplies, multimeters, right? Some of you might have, some of you might not have, but you're definitely going to use it for 145. Okay. So when you are in the lab and you are working with a benchtop power supply, it's supplying some voltage. It might also supply some current. They both go hand in hand. If you have a circuit that is being supplied voltage, it is also receiving current, or if you're supplying current, it is also receiving voltage. You cannot have one without the other. Okay. So what's the difference between a voltage source and a current source? It's simply the mode of operation. If you look at these lab benches behind us, there are some triple power supplies or triple channel power supplies that are on the bench top. Okay. And you'll see something similar in the labs that you're going to go work in. Might be slightly different manufacturer, so model might be different, but the principles of operation are the same. So you have a power supply, and that power supply is supplying voltage and current. If you fix the value of the voltage, then it is functioning in a mode that is known as constant voltage mode. And you might see a small CV in some corner of the screen. So if it's in CV mode, we say it is a voltage source. Okay. So CV mode stands for constant voltage, and we refer to it as a voltage source. And I'll explain how we can tell the difference. There's another mode known as CC mode. In CC mode, we program the output or desired current into the power supply. And so now it runs in constant current mode, and we refer to that as a current source. That's the only difference. There is no other difference between a voltage source and a current source. Okay. Let's take a pause. And for that, let me know if you have any questions. Okay. Let's look at an example. So let's say I have a source. What kind of source is this? Voltage source. This voltage source is rated for 10 volts, and I connect it to this resistance that is of 1 ohm. So based on Ohm's law, you don't have to write or draw anything out, but what do you think is my current through the resistor? And V equals IR, so 10 amps, right? Now let's say I connect a 10 ohm resistor. What is my current now? 1 amp, right? V equals IR, so 1 amp. What is the difference in voltage between the first resistor and the second? They're the same, no change. They're constant. So in constant voltage mode, the power supply unit will keep the voltage constant, but it will change the current based on the load requirement. Okay, we have a power supply. I'm going to set 10 volts, run in constant voltage mode. Say 10 volts, and I connect a 1 ohm resistor. It's going to supply 10 amps of current. Now I change the load to 10 ohms. Constant voltage mode means it's still going to supply 10 volts, and now it will change the current only to 1 amp. If you change it to 100 ohm load, voltage will still remain constant at 10 volts. The current would be changed to 0.1 amp. And that is what makes it a voltage source. That's it, nothing else. Let's take a pause and let me know if you have any questions. All good? So let's talk about current source. What do you think happens in a current source? Based on the same definition of a voltage source, what will a current source do? Absolutely. Current source, meaning it's running in constant current mode. So it'll keep the output current constant, but it'll change the output voltage depending on the requirement of the load. That's the only difference between a voltage source and a current source. In real life, it is one and the same thing. It's the exact same box that we're going to use for the entire quarter, actually for the rest of your year. So let's say we have a 1 amp current source, and we connect a 1 ohm resistor to this. So the voltage would be 1 volt. If you change the resistance to 10 ohms, the voltage would be 10 volts. If you change the resistor to 100 ohms, the voltage would be 100 volts. What if you change it to a 1 kilo ohm resistance? How much voltage would you expect? 1000 volts, absolutely. The reason I bring up that example is because 1 kilo ohm resistors are some of the most common resistors you will use in the labs. But do you think any of these power supplies go up to 1000 volts? No. So real life power supplies might go up to like 20, 25, or these ones go up to like 30 volts. Okay, that's the max limit. So also the resistor itself that we are using would not be able to withstand that much energy. Right? Electrical energy power is a product of voltage and current. So 1000 volts, meaning 1000 times 1 gives us, million watts. Resistors are like quarter watt resistors. So there is a current limit and a voltage limit that is set on every power supply. If you're running in constant voltage mode, you always must set a current limit because you don't want your circuit to be blown up. Okay, so this is some practical knowledge that you need to use when you're in the lab. Constant voltage mode, always set a current limit. Constant current mode, always set a voltage limit. And that would be provided to you in the lab instructions. But just as an engineer, this is some fundamental knowledge that you should take with you. Okay. So always set current limit. And here you would always set voltage limit. So it's kept constant, so you get a straight line. Okay, voltage is a straight line, current would be a straight line. Right, how are we doing on time? 20 minutes. Okay. Battery is an example of a voltage source. We cannot change or we cannot set or program current in a battery. So battery is an example of a DC voltage source. Okay, it provides an output voltage that is constant. Sometimes a battery is also represented by this symbol. Two horizontal lines, one long, one small, that indicates a DC battery or a DC voltage source. Okay. And then, of course, these are the power supplies that you will encounter in the labs here in the EE and CPE department. You may have already used something similar to this. Other classes? No? Okay, yeah. Anyway, so this one is a 3-channel power supply. You can see right here, 1, 2, 3. The ones that are on the back in this room, they're also a triple channel power supply. So you can take 3 independent power supplies coming out. 2 of them would be able to go up to like 30 volts. The third one can only go up to like 6 volts. That's for digital logic circuits because we work primarily with voltages less than 6 volts in digital circuits. So anytime you're using a manufacturer's power supply, you always want to note whether that channel can supply more than 6 or not. Okay. Some manufacturers use channel number 3 for 6 volts. Some of them use channel 1 for 6 volts. Something to keep in mind. Okay. All right. So as I was saying, a battery can only function as a constant voltage source, whereas a programmable power supply that we use in the lab can be worked as both voltage as well as current sources. All right, other functions that we'll look at when we work with diodes. Diode is a non-linear device. Okay, a diode is a non-linear device. Again, we're not going too much into the physics of the device or the workings of the device. We're not looking too much at the characteristics of the diodes, but we would like to inform students that a diode voltage and current have a nonlinear relationship defined by the exponent function. So that is another thing that we are going to study in this course. Okay. The diode equation is given right here. This is known industry-wide as the diode equation, or it is also known as, does anybody know what it might be called? I wouldn't expect it anyway. It's known as the Shockley equation. It's named after William Shockley. William Shockley, Walter Brattain, and John Bardeen. There were 3 scientists working at Bell Labs. In 1947, they presented the first working prototype of a solid-state device, which was the germanium transistor. And they were awarded the Nobel Prize for this discovery and invention. Okay, and so William Shockley did a lot of the work and developed this equation. So this equation was attributed and given his name in his honor. Again, this is not something that we need to study for the class, but it's something that you need to know. All right. In the lab specifically, you're going to use LEDs and photodiodes. Well, actually, let me back up. This is the symbol of a diode. It's a triangular arrowhead with a line at the tip of the arrow. Okay. The name diode comes from the fact that this was the semiconductor version of a vacuum tube diode. Diode stands for 2 electrodes. So the first vacuum tube had 2 electrodes, 1 anode, 1 cathode. And so the first vacuum tube electrode, sealed vacuum tube glass chamber, was named as diode because it has 2 electrodes. When they created the semiconductor version of the diode, they carried over the nomenclature, hence the name diode for this solid-state device. Also, the name of the 2 terminals were also carried over. And so these were labeled as the anode and the cathode. Okay, anode and cathode. And all comes back from the fact that it was it was a semiconductor version of a vacuum tube diode. Then there are light emitting diodes, hence LED acronym. And then this is known as the Schottky diode, named after the person who invented it, Schottky. If you see a symbol that looks like this, which is a diode, and you have light falling or coming into the diode, it's representing a photodiode that receives the light. An example of a photodiode is also a solar cell. Solar cell receives light, photons the photon energy is converted into electrical energy. Photons strike the surface panel, transfer their energy into the electrons of the semiconductor material. So energy transfer takes place. A lot of the energy is lost in conversion, and solar cells are not very efficient. So that would be a photodiode, one kind of photodiode. And if it's emitting light, then it's a light emitting diode. There is another special kind of diode where the cathode has whiskers. And this diode is known as the Zener diode. Zener diode. Okay. A diode is a nonlinear and one-way device. Okay. Current flows only from anode to cathode. Anode to cathode. Okay. All right. Any questions before I move on to the next slide? Okay. Let's look at another function, which is now a periodic in nature. So periodic functions. Okay. Now, periodic functions of time. When we say function, we simply refer to the graphical representation of any quantity, whether it's voltage or current or power or energy. Here, let's say we refer to voltage or current or power or energy. And here I think, well, it's not specified. Let's just say it's voltage, okay? What it means is this periodic function or time varying function changes its value at any given point in time. It does not have a fixed value. Okay, at any given point in time, if you sample the voltage, the value would be different. Okay. What you see here in this illustration, in this image, is known as a sinusoidal waveform. This is known as a sinusoidal waveform. Mathematically represented with the sine or cosine function. Sine or cosine. Oh, right there at the top. So mathematically, it's just sine or cos. And we use those to solve our equations in our systems. Okay. So here we have this function where we are representing y equals a sine omega t. A stands for the peak value. So the highest peak, which is right here, that is A. Okay, it does not stand for amps. I want to clarify that. It does not stand for amps, it's just a constant value. Actually, let's stay away from the word constant. Simply the value, the peak value of the waveform. It's basically the highest value of that waveform. Okay. Now, the reason we are talking about this is because this is the form we obtain when we generate electricity. Okay. Electricity is generated when we have a coil of wire rotating inside a magnetic field. And so when it rotates, it's moving between the north and south pole of that magnetic field. So the way the electrons move and the waveform that is generated, it goes to the north, south, north, south, north, south. And that's why we have that kind of shape for that waveform. And mathematically, it turns out it's a sinusoidal waveform. Okay. So all electricity generation, distribution, transmission, distribution, and usage is sinusoidal. This is also the waveform that comes out of our power outlets worldwide. And it's referred to as alternating current, or AC. The reason they came up with that name was because the sinusoidal waveform for electricity alternated between a positive peak and a negative peak. And so they call it alternating current. But in general terms, we use the terms AC and DC as words themselves. We do not use it as an acronym, because we sometimes use AC voltage, AC current, DC voltage, DC current. If we expand the acronym AC, it becomes alternating current voltage, alternating current current, or direct current current, which doesn't kind of make sense. So we use AC and DC simply as words and not as acronyms. Direct current simply means it has a constant value with respect to time. It doesn't change. AC simply means it could have any value at any given point in time. AC waveforms are not restricted to sinusoidal. Could be any waveform. Be triangular, could be rectangular, could be square, could be arbitrary noise. Okay. The sound waves that are captured when I'm speaking, if you were to observe this on the oscilloscope, you would see sinusoidal waveforms at multiple different frequencies. Okay, because every time we speak, we're generating sound waves. The sound waves have a particular frequency and form, but all waveforms can be represented as multiples of a sinusoidal waveform. So let's talk about this mathematical equation right here. We have A sine omega t. The omega comes from the fact that it's a unit circle. And then the length of this, actually, let's stick with A. Peak value of that voltage is A. This length is also A. Okay. So this mathematically is represented as a vector that is rotating in the complex plane in a counterclockwise motion, going in this direction with a speed of omega. So this is the lowercase omega. That omega stands for the angular frequency or angular velocity. Units are radians per second. Omega mathematically can be given as 2 pi f. F is the frequency of the waveform, and the frequency of the waveform is basically how many times does the waveform repeat itself in 1 second. Okay. X-axis is always time. And one cycle is the point at which the waveform starts repeating itself. Still have 4 or 5 minutes. So this is one cycle, or also known as the time period of the waveform, T. Time period of the waveform. So the waveform starts at 0, goes to a positive peak A, comes back down to 0, then goes to a negative peak minus A, and comes back up to positive. And that point, it's going to start repeating itself. So from that point on, it's going to go back to a positive peak of A. So the point where it begins to repeat itself, and hence the name periodic, the point where it begins to repeat itself is known as one full cycle. Okay. The number of cycles that this waveform takes in 1 second is defined as the frequency of the waveform. One cycle is also noted as the time period of the waveform in seconds and uppercase T. Time period, units are seconds. Frequency is unit is hertz, and frequency is the number of cycles per second. The relationship between frequency and time period is that they are inverse of each other. So F is 1 over T, T is 1 over F. Uppercase T is different than the lowercase t. Okay. What is the frequency of the power outlets? 60 hertz in North America. What is the voltage? Anyone? 120 volts. It's a general knowledge question. In North America, the power outlets are 120 volts and 60 hertz. Almost the entire rest of the world outside of Japan and a few other countries, the power outlets are 220 to 240 volts and 50 hertz frequency. 60 hertz means the power outlet voltage is going from 0 to a peak value, back to negative value, back up to 0, 60 times in 1 second. That's why if you ever stuck your finger in a power outlet, which I don't recommend you do, you get a zing or zapped feeling because it's changing its value. If it's DC, you get stuck. You can't pull yourself off. Okay. 120 is also not the value of the peak. Okay, 120 is an RMS value, which is something that we'll look at later. It's sort of like an average value. The actual peak value would be 169 volts. Okay, so at any given point in time, 60 times in 1 second, the value of the voltage in the power outlet goes to 0. Actually, 120 times because it's going from 0 back to 0 and then back to 0. So 2 times in 1 second. Okay, and that's what makes it periodic in nature. One final note about this is that what was I saying? 60 hertz. Does it seem like a very high number? Right? It's actually very, 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 very low frequency. Most people can't even probably hear. I definitely cannot hear that low anymore. That's basically what we call a subwoofer frequency. Okay, subwoofer frequency is also 100 or 150 hertz. If you think about it, AM radio transmission takes place in the kilohertz range. Kilohertz is 100,000, 600,000, 700,000 range. The call sign of a radio station is basically the broadcasting frequency for that station. So AM 630 AM simply means the broadcasting frequency is 630 kilohertz. 101.7 FM means it's broadcasting at a frequency of 101.7 megahertz, 10 raised to 6. There's mobile communication, satellite communication. They all go in the gigahertz range. Your wireless routers are gigahertz frequency. Those are high frequency. Okay. 60 hertz is considered very low, even though it seems very high compared to everything else. All right, we'll end class here today. I haven't yet set up the video playlist. That's on my agenda of things to do today. So today after class, around 5 p.m. or 6 p.m., I'll have the playlist set up, and then I'll have the videos uploaded on there. If you have any questions, come see me anytime you want. Send me an email. Happy to meet students anytime.